I'm going to talk a bit about immutability or putting the dream machine to work. I don't know how many people are familiar with some of the things I'm going to be talking about. It's better if you aren't. But anyways, let's get started. So who am I? I'm basically a front-end JavaScript developer, or that's what I've been doing for a very long time. I was at the New York Times for 4 years. I worked for the Modern Museum of Art, the Whitney Museum of Art, doing front-end development things. I recently left the New York Times to work for a company called Cognitect. Cognitect is sort of the steward of a programming language called Clojure, which sort of embraces functional programming and immutable data structures. It's a Lisp. It's pretty interesting. Runs in the JVM and also runs on JavaScript. I'm actually one of the lead maintainers of ClojureScript, which is the implementation of Clojure that targets modern JavaScript engines. So Cognitect sort of stewards ClojureScript, and we also have a very interesting database product called Datomic, which takes these sort of same ideas I'm going to talk about, this notion of persistent data structures, and applying them to disks. This might sound very esoteric, but I suspect more than 50% of the audience probably uses Git. Git is also designed around persistent data structures, but it's disk-oriented. We're going to look at persistent data structures that are oriented around things in memory. Okay, so I'm not going to talk actually that much about Clojure or Datomic or ClojureScript. I'm actually going to talk about the big concepts. It's really exciting. I actually blogged about this stuff around December. Since then, there's a framework called React. React has gotten a lot of traction. It's been growing very rapidly, somewhat based on the things I've talked about. And people are actually starting to adopt many of the things that I'm going to present. So when I gave this talk, a version of this talk, way back in March, it was still not quite catching on, but things have significantly changed in that time. And we'll see that at the end. Okay, so this talk is about user interfaces and how I think we can radically change the way we program user interfaces. For me, this sort of starts with The Dream Machine. This is an amazing book. This was actually recommended by Alan Kay on his mailing list, The Foundations of New Computing. Great mailing list. It's kind of not so great now, but the archives are amazing. But anyways, on this mailing list, he suggests this is the book. If you're interested in where did user interfaces come from, object-oriented programming, the internet, this story sort of lays down all the characters and all the events that allowed interactive computing to sort of come to be. I think our notion of computing is highly informed by the fact that interactive computing took off. It wasn't obvious that interactive computing was a good idea. A lot of things had to happen. So the book actually talks about the very interesting person who was not a computer programmer. This is J.C.R. Licklider. He was a psychologist. And he was he saw the importance of computing, but he was also very convinced that we weren't going to get very far if we didn't start thinking about psychology and human factors and how these things could shape our understanding of computers. He was sort of integral in the design of one of the very first interactive graphical user interfaces. He also sort of stewarded ARPA, which was a sort of somewhat related to defense program that funneled money into universities to push interactive computing forward. So it was due to people like him that, Xerox PARC, Alan Kay's group there, Douglas Engelbart, who's famous for the mother of all demos. It was Licklider who believed that these people had interesting ideas that should be pursued. You can sort of skim over this, but what's interesting about this is Licklider wrote a very important paper 54 years ago called The Man-Computer Symbiosis, where he was sort of, at the time, this was pie-in-the-sky stuff, how are we going to make computers usable by all people, and how are we going to connect people through computing? And that's what this paper is about. What's interesting is that he points out that a particular type of data structure might have an important role in the design of computer user interfaces. And so my talk, in some sense, is just convincing you of what he had said 54 years ago, that tree-based data structures are actually extremely well-suited in sort of as an element in the design of sort of the architecture of user interface programs. And we'll see that. So here's an interesting photo. This is John McCarthy on the second from the left. He invented Lisp. garbage collection, interpreters, functional programming, recursive programming, a lot of things all at once with Lisp. To his right is probably somebody people are less familiar with. That's Ed Fredkin. He invented the tree. It's written, you'll often see it written in English at least, T-R-I-E. People will often say try to distinguish between tree, T-R-E-E, and T-R-I-E. But Ed says, actually, you pronounce it tree. It comes from retrieval, which in English is R-T-R-I-E-V-A-L. So Ed invented the tree, an extremely important data structure, and we'll see that. So yeah, and then also these, John McCarthy got funded through ARPA. Ed's research did, Alan Kay's research. And Alan Kay took, actually, a lot of the ideas that John McCarthy came up with, interactive computing, dynamic compilation, all this stuff, and sort of took it to the next level with object-oriented programming in a way that actually is very recognizable today. If you fired up a Smalltalk virtual machine, which you can, there's a really great one called Squeak. It's widely available, open source. You can download it and run it. If you open up a system browser, which sort of gives you a window into exactly how the system works, you would see some very familiar terminology. If you come from a user interface programming background, you're very familiar with the terms model view controller. So especially if you're doing front-end JavaScript, this is all the rage these days. Lots of competing MVC frameworks. Long shadow. So similar to the tree, how important the tree is. The tree is 54 years old, and I'm going to show you there's a lot more to it than you might think. But MVC is really old, 1979. That was the year I was born. So 35 years old, these ideas around how do we organize user interface programs. Long shadow, basic concepts, still prevalent. And I think that's because, of course, at an abstract level, MVC is very sound. It's a sound separation of concerns. But what I'm going to try to question is that I believe that implementations leave much to be desired. And this has to do with the fact that people continue to sort of design their programs around stateful objects. And so a lot of what I'm going to demonstrate is that on modern hardware, with the amount of research that's gone into persistent data structures, you can organize your programs in a completely different way and eliminate stateful objects. You can still have modular, object-oriented programs, and there don't need to be any stateful objects anywhere. We'll see that. So the first half is sort of going to be like just a quick data structure review, because I'm not sure how many people are familiar with persistent data structures. The last half will be sort of like showing demos of these ideas actually being used in production by different people and different companies. So I'm not going to, these next series of slides are not my own. They were done by a really cool guy called Zach Allen. He's a facilitator at this thing called Hacker School in New York. It's sort of a writer's retreat, kind of like a writer's retreat, except it's for computer programmers. You can go there. It lasts 3 months. But he's there as a facilitator, and he wrote some really incredible slides describing how persistent data structures work. I'm just going to reuse them. They're very good. So let's get into how does a persistent data structure work? What does a tree have to do with an immutable data structure? So even if you don't believe in functional programming, we still want to understand the value of this particular idea, the idea of the persistent data structure, because often even if we don't adopt the functional mindset, there may be still something of value in that paradigm that we may be able to appropriate. And I think persistent data structures definitely are one of those things. So functional programmers, they don't like the immutable objects. They like dealing with immutable values. It gives them, sort of deep mathematical reasoning about the code. That's why they like this. The whole idea is that when you change something, you return a new value. You leave the old one unmodified. The poor man's immutable data structure is copy on write. Copy on write works for very small things. It doesn't work when your data set increases in size. So we'll see how we can account for that. We say persistent. This is an overloaded term. Often when people say persistent, they mean on disk. In this sort of context, we're just saying that when you get an updated value, you don't destroy the previous value. So if you have a mutable array and you mutate it, that array represented some value, and when you mutate it, you destroyed whatever value it previously represented in order to get whatever new value that it represents. Something that's interesting about persistent data structures is that they're fast. This is within the past 15 years. So prior to the early 2000s, there were some interesting, like Okazaki has a really great survey, but it really was not until Phil Bagwell's work showed that you could get much better than paper complexity. You could actually get performance that is near competitive with mutable data structures for many applications. Okay, so what is a persistent data structure? I'm sure that everybody knows about the linked list. Using a linked list in sort of a disciplined way is actually the simplest persistent data structure you can have. Linked lists, even though they seem so simple, actually have some properties that I think are often overlooked. So here I have a linked list. It starts with some element, and each cell points to the next thing. This is something that I think we've all seen. What's interesting, though, is if you cons a cell onto the head of this particular linked list, we have a new value, right? We have the original value, which was whatever 4 values there were, and then we get a new list that represents some other value that has 5 elements in it. All those gray circles, though, that's shared. That's memory is shared, right? So this is what's cool about lists, is that they share structure. It's very efficient to add something to the head of a list, and it's also very memory efficient. You can even get the tail of that first list and then cons a different head onto it. You have 3 distinct values, but they share more than 50% of their memory. So you can actually do some interesting tricks if you move away from linked lists, and we'll see the most basic example of this. So structural sharing is the big idea behind persistent data structures. It's also, if you're familiar with how Git works, that's how Git, you basically, if you update some file, Git doesn't record deltas, it just rewrites that blob, and then most of the tree that represents your source structure, your source directory structure, is shared between different commits, different trees. Okay, so you get space efficiency, you get computational efficiency because you're avoiding copying. We're not doing copy on write. So Phil Bagwell was the man who really showed that there's a fast way to do this. There are 2 papers he wrote. One was on the array map tree, and the other was on the hash array map tree. Both of these actually were not of the immutable variety, but the ideas were already in place. It was actually Rich Hickey who took Phil's research that showed this kind of data structure could perform well. Rich modified a couple of things and made them the centerpiece of Clojure. And one of these persistent data structures based off Phil's work is called the Bitmapped vector tree. It's one of the easiest to explain. And you will see very quickly how you get all these interesting properties based on their design. Data in a bitmap vector tree, data lives in the tree, data lives in the leaves. It's a prefix tree. We'll see what that means here in a second. It's a bitwise tree also. We'll see that in a second. We're going to see some pretty images for this stuff. Okay, a persistent vector. So what a persistent vector is, synonymous with bitmap vector tree, is that it's an array of arrays. You structure your data as an array of arrays. You pick some dimension n, doesn't matter. Just for now, we're going to pick some arbitrary size. We're going to keep it small so we can have nice graphs on the screen. So let's pick size 4. So every element of this root, this is the root node, is going to simply point to more arrays of the same dimension. Those arrays will point to more arrays of the same dimension. And finally, we'll have the last level, which are the leaves. And that's where the contents, the actual contents of the data structure will live. So this is what it looks like. Well, then you're like, well, okay, that's interesting, but how do I find anything in it? So you have this funny property, is like if you want to find the 106th element, 106 is an integer. 106 actually has a bit representation, and you can actually mask the bits to find that particular thing. So I can mask the first 2 bits. The first 2 bits tell me to look at index 1, counting from 0. The next 2 bits say look at index 2, counting from 0. Again 2, again 2. There are no bits left to mask. We know we're done, and then we know we have the number 106. We know which thing to pick out. So if you're familiar with, modern compilers, even especially modern JavaScript compilers, these things will get converted into assembly instructions for x86, 64. We're talking about a couple of bitmask operations and a couple of array accesses. If these arrays are being accessed frequently, then you get really nice cache properties. Okay, what about updating? So how are we actually doing better than copy on write? We do something very simple. We have the path, right? 106 represents the path. This is the whole prefix tree, the bitwise prefix that we were talking about earlier. 106 gives us the path. We simply have to replace all the arrays on the path. And at the end, we replace 106 with the string foo, right? So notice that this could be a huge data structure. We only had to, at most, copy and replace 4 of the arrays in that structure. So a very, very large amount of structure can be shared with persistent vectors. So let's start thinking about, well, obviously this is probably dependent on the size that we picked. So length 4, that's probably not a good one. It turns out that 32 is a really great one. This is based on empirical evidence on modern hardware. 32 gives you a nice sweet spot between how long does it take me to find something or how long does it take me to update something in that data structure. But also 32 is a very wide branching factor to get a sense of how big that is, that branching factor. 32 to the 7th power is 34 billion elements. So like, 64-bit VM, 64-bit virtual machine for JavaScript or Java. This is, even if it was a flat array, you're talking about 256 gigabytes of RAM. We're just now getting to the point where like that's something you would deploy on the cloud maybe, but definitely way beyond the memory capacity of most of the laptops that people are carrying. So you can do a lot. So at most in this data structure, you would have to do 7-bit operations, 7 array lookups to find any element. To update this massive data structure, at most you'd have to copy 7 arrays that have 32 elements each. And this is just a mem copy. This is very fast. Okay, so that's a lot of talk. Let's see some numbers. A little simple demo. So this is running a recent build of V8. I do a lot of ClojureScript development, so I compile all the JavaScript engines at the command line because it's easier to benchmark. Ooh, sorry, that's not nice. I'm gonna turn that down for now. Okay, so this benchmark is very simple. It's naive, but at least it will still demonstrate an interesting property, which is that we're going to build a mutable JavaScript array. So a mutable JavaScript array you can just push until you grow it to a certain size. We're going to just add 1 million integers to an array, and then we're going to see how much slower is it to build a persistent vector. So it's not the same. In the mutable version, we're actually mutating the same array, growing it. In the immutable version, we're actually going to create 1 million vectors to get the final vector that we want. So this is an old laptop. This laptop's 4 years old. So it takes 204 milliseconds to push onto a mutable array with V8. It takes 391 milliseconds to do it with an immutable vector, which is already very shocking, right? It's just shy of 2 times slower, which is more than fast enough for many applications. One of the slowest operations you can do is query the DOM. Many JavaScript programs simply query the DOM, which is why they're really slow. But we can do better than that because we've been, the Clojure community specifically has been studying persistent data structures for 9 years now. So we have a lot of optimizations in place. One of these is the notion of batching. So what we can do is we can actually take a persistent vector, in 01 time convert it into something mutable, batch a bunch of updates to it, and in 01 time convert it back to something persistent. And you can get really big performance wins. So how fast is this when we do that? See this? So the array 1 will be about the same. It's faster. It's faster to do batching operations on a persistent vector than it is to use the built-in mutable array. Of course, the performance characteristics are different on every engine, but everybody's fighting to be the fastest. So this is a recent build of JavaScript Core, which is Apple's engine. Not bad. It's still a little bit faster. So that's pretty interesting. So you can actually see that it would be realistic to construct an entire program used around immutable data structures because the performance loss is not really that interesting. The biggest thing you want to worry about when you use them, of course, is GC. That's definitely the trade-off. There are cases where the type of thing you're building, GC is going to be a problem, and you might want to do something else. But there are lots of programs where that's not an issue. Okay, so yeah, again, JavaScript engines are getting faster. The way that we've written these, our data structures are only going to continue to improve. That was the research around V8, which is all the work around optimizing dynamically typed object-oriented programs. It's getting even crazier these days with things like JavaScript Core, where they're doing very fancy things like taking polymorphic code and devirtualizing it so that it's monomorphic. So all these things will make the types of programs that we're designing ClojureScript around only be faster. Okay, so now that we know about persistent data structures, what's the point? So now I'm going to demo. So the sort of insight that I had was that now that we can see that they're useful and they're fast and have these interesting properties, what if we design a UI around them? So I wrote a library called Ohm last December. It was an experiment, and excitingly, it's actually kicked off a lot of similar research in the JavaScript community, which is really exciting because the ideas are now filtering outside of the sort of more esoteric functional programming world. So what is Ohm? Ohm is pairing the persistent data structures of ClojureScript with the React sort of library, really, from Facebook. Raise your hand if you've ever used React. Oh, good. So raise your hand if you've heard of React. Okay, good. So that's pretty cool. A lot of people have heard of it. So the neat thing about React, there are a lot of neat things about it, but the part that I cared about when I encountered it is that React, even though it presents this sort of object-oriented veneer, was designed by a functional programmer. Because conceptually what it does, it allows you to take data, apply a function, and then it computes a virtual DOM. So you don't actually get to touch the DOM or query to the DOM or manipulate the DOM. You apply a function to some data, it produces a virtual DOM, and React will use the virtual DOM to actually generate whatever the real DOM needs to be. And it picks the most efficient thing, whether that's generating strings or whether that's actually mutating nodes. The other neat thing that it does, kind of like a graphics engine, because again, querying the DOM is so slow, it's catastrophically slow, what it does is that it actually does the diff and produces the minimal set of changes and applies them all at once. It's a complete anti-pattern in JavaScript programs to run a query, mutate the DOM, run a query, mutate the DOM. That's like one of the biggest bottlenecks. And React just gets you out of that world completely. But where it gets more interesting is that, so when you get change in React, what do? You just have different data. And React will compute a different virtual DOM. And what React actually does is it takes virtual DOM 0 and virtual DOM 1, it runs a diff on it, and again, it calculates the minimal change set. But the beautiful thing about React, and this is why I got so excited about it, is given that's exactly how it works, it's very simple to flip V1 and V0, and React will give you the reverse set of changes for free. There's no work that you actually have to do. It's just a property of that model, the React model. So I wrote a little short little program where I demoed like you could do MVC, which is like a popular benchmark. I think it's stupid, but whatever. People want to benchmark, MVC programs want to do MVC. But I showed that I could add full undo and redo to do MVC in about 5 lines of code. And people were sort of surprised by that because doing undo generally with UI programs is a nightmare. If you don't plan ahead for it, it's never going to happen. But a really cool developer from Ableton actually saw my post and said, I don't really believe this guy. And so he decided he was going to make a 64 by 64 pixel editor called Goya, in which that it would have very sophisticated undo features. And he wanted to see, well, how much complexity is that going to create for my program? Goya is very cool. It's a fairly sizable app, but this is it. I can draw some pictures around this guy. On the right, you see history accumulating. I can undo. I can click redo. I can do this all day, and this is not going to slow down. And you notice that on the left, you've got, I can scrub over the history. You've got the little guy. I can actually export this as an animated GIF, et cetera, et cetera. It's a cool little pixel app. So how much time did he spend to add undo, redo, export it as animated GIF, and the sort of scrubbing preview? 60 lines of code. This is the whole thing. Very small, simple functions, right? And this is because what he's done is he's committed to putting his entire app state into one data structure, one persistent data structure. And again, because the way that persistent data structures work, you never destroy the previous thing. You get perfect snapshotting. It's just a property of the data structure itself. And you also get very efficient diffing because you can do this neat trick where you know two things are equal if the pointers in memory are the same. And you know that they've changed because the pointers will be different. React can't play this game because the data structures that they use, or that JavaScript programmers use, are objects and arrays. And the only way to know if something changed is to walk the whole thing. Persistent data structures, you don't have to walk the whole thing. If the pointers are the same, there's nothing to walk. So then you're probably, okay, so a lot less code, but what about the memory, sort of the memory? What, okay, it's fast, it's, time is good. It seems to decrease some complexity, at least in some parts of applications. But how much memory does it use? So what I did, I made a demo where I said, well, what if I did a full array copy and I recorded 1,000 frames, and then I did an update of a vector 1,000 times, and I saved each copy of that persistent vector. How much memory does it take to save 1,000 vectors where it's 4,096 elements and I'm updating 1 pixel, right? Just kind of like what a user might do. And then compare that to just actually copying an array 1,000 times. On the left, you can see that I did a Google Chrome heap snapshot. It's really awesome. And I said I snapshot the application before I start doing the activity. I do my activity, and then I do another heap snapshot. How much memory is being used? So on the left, you have persistent data structures. It takes 0.2 of a megabyte to do 1,000 snapshots. On the right, I have full array copies 1,000 times where I've changed 1 pixel, and it's 1.7 megabytes. So it's nearly 10 times less memory to use a persistent data structure for this. So again, all the points, bullet points from earlier about persistent data structures, they're fast, they're more memory efficient. These all come to pass. You can run profilers and see this to great effect. So, early on, people often would be like, well, what is this good for? Undo is kind of neat, but lots of applications don't need that. I actually think that undo is actually, of course, very useful for many types of applications, but any application where you have sophisticated error handling, where you might want to roll back the state of your app, you do an optimistic commit, you update the UI, it fails in the server, and you want to just rewind the state of your application. You see tons of code bases where you have manual rewinding of the state because A, they didn't want to write an undo system, right? And so you just have manual copy and pasted code like we're going to recover the state of our app before we did the optimistic commit and it failed, right? So persistent data structures just give you a free ride. You can just be like, this might fail, let's save the state now. It failed, let's just reload that state. Done, there's nothing else to do. But there are other cool properties that other people are exploring. There's a really interesting project called Elm. And Elm actually is using this to do time travel debugging, where basically you can, in a live program, modify the program, update the code, like hot swap it, and without corrupting any of the recorded states. And this is really, really awesome. So there's huge debugging properties. And actually, we'll see this in the context of Elm in a second. So there are lots of things. And in fact, I don't even know. It's a whole new frame of mind. And people are just starting to see the implications when they start organizing their programs differently. One thing to encourage this exploration that I started 2 years ago that people didn't care about was something called Mori at the time. And then now it's actually quite popular. Actually, Meteor.js uses it to do dependency resolution for their package manager. And that's really neat. This is just an image of, more people are using it these days. But Facebook, more importantly, released a new persistent data structure library. So they're doubling down because they've seen that Ohm can actually beat React at its own game because we can do diffs faster. Again, because we have faster quality checks. So to do MVC in Ohm is like twice as fast to render as React because of persistent data structures. So because I demonstrated that, Facebook is actually doubling down on persistent data structures. They have their own library that's a little bit more idiomatic than Mori. Mori sort of shows its ClojureScript roots. And this is fine. I think this is great. The more work and the more thought that goes into persistent data structures and sort of marrying them with UI development, it's a good thing. So another thing that's pretty interesting is that once you go this route, you know, JavaScript programmers have been sort of locked into this like ridiculously narrow vision of data structures where the only thing they think exists are objects and arrays, and that's not true. But a lot of that is because there's a convenience around that, and that's JSON, right? So in some sense, JSON has prevented JavaScript from moving much further because if you can't put it on the wire, it's kind of a pain in the ass. So actually at Cognitect, we worked on this problem because we actually needed it for something else. So we wrote a thing called Transit, which allows you to hijack JSON and do an extensible encoding for data structures. And so I demonstrated that that's actually really great for immutable JS. You can actually decode JSON into immutable JS data structures, even though you're sending regular JSON over the wire. And it's fast. On all the engines, the performance hit over JSON is uninteresting. Okay, so Meteor.js is using it. It's really cool. Prismatic actually is using Ohm. They actually do that. I'm going to show a really cool demo from Circle CI, which also uses Ohm. There are a bunch of people using Ohm. There's actually quite a few Ohm-inspired things now in the React world. There's something called Omniscient. Again, React is also picking up some aspects of the sort of Ohm philosophy. I just want to show one other demo. And this is Circle CI. And they did something really cool. For those of you that are familiar with React, React has this very interesting split between what I would call global state, global app state, and something called component local state. Because you often want to divide the two. You often want state to be local to a component. This is the whole modularity, hiding the state thing that people like about object-oriented programs, which is a good thing. The object knows about some state and it's local to it. But really, my argument would be that what's useful is the illusion of this, not the actual hiding of state. As long as you get to program as if your state was hidden, great. But you don't actually need real hidden state. And Circle CI took a little gist that I had made, a little example where I showed that you can actually modify Ohm so that all component local state gets written into the global app state. And they actually push this to production. Nothing broke because it doesn't change the semantics. There's no semantic changes. Again, you wrote the code as if there was local state. Who cares if it was real or not? And this is a really neat demo showing what they can do now. Since now that all state of their application, every state, whether that's toggles, whether that's the position of something on the screen, it's all snapshotable. They can do some neat things. I'm going to play this short video.
Hi, I'm Daniel from Circle CI. I'm going to do a quick demo to show you what's possible now that we've taken React State Service and mounted it into Ohm's global app state. So on the left here I have Chrome. I'm on the Add Projects page. I'm going to type something in this input to filter repos. Now this input is stored as component local state, so it's transient, normally. I'm going to hit a keyboard combination to save the state. I took the global app state atom, serialized it to a string, and then stored it in this state string variable. This makes it easy to copy to my clipboard, and now it's in my clipboard. I'm going to come over to Firefox. I'm going to hit another keyboard combination. It's going to bring up this prompt. I'm going to paste the app state string in there. When I hit OK, it's going to take that string, it's going to deserialize it, and then it's going to reset the app state atom. And so you can see it's restored all the state, even the normally transient input state. So we're pretty excited about what we can do with this. You could, instead of sending screenshots to demonstrate a bug, just send the app state. But if you have a designer, you want to show them an edge case, don't give them a list of steps to reproduce, just give them the app state.
Okay, so that was a lot of stuff. Hopefully you found some of that interesting. I'm assuming they will send out the slides, and I've included links. Yeah, so things I think that are cool to look at, regardless of whether you use any of these things. I think there's an amazing sort of surge of ideas around this because I think these ideas can actually go a very long way, and we don't really know the limits. But definitely, I recommend checking out ClojureScript. Definitely looking at React if you've not looked at it before. Looking at Ohm, even if you never planned on using it. I think there are lots of interesting things to think about. That it demonstrates Transit.js. If you're starting to think that like we want more data structures and we want a way to get them efficiently to the client, Transit.js is something that we wrote to solve that problem. It's very fast. Mori, again, if you want to play around with persistent data structures from JavaScript, Mori is a great thing. Immutable.js has come a very long way. I think it's been out for 4 or 5 months. It's getting really, really good now. Also a great option if you want something that's more idiomatic as far as JavaScript is concerned. So I think I'm done. I'll take questions if there are any. No questions? Go ahead.
Hi. So I've done a lot of playing around with Elm, and I think it's a really cool library. I have yet to play with Ohm, so hopefully I can do that soon. But I'm wondering what you think about the idea of if you have persistent data structures, like why stop there? Why not keep your entire state of your entire application persistent? And sort of, instead of mutating the state of your entire application, also have that be persistent? Or did I misunderstand something?
So the Ohm model is that model. All the app state is in one data structure. That is the model.
So are you sort of, like, I know in Elm, basically you're like folding over that state and producing new states based on previous states? Is that what you're also doing?
We don't adopt the FRP philosophy. Okay. We're much less religious about that. I mean, the only thing we really care about is the global app state pattern. The other FRP things are sort of separate, in my mind, a separate topic, because you can get a lot of value without having to fold over the app state.
This is somewhat loosely related, but there is actually now people try to do this with systems actually with Nixos, which is I don't know if you've heard of it, which tries to solve the problem of system upgrades and system configuration upgrades and package management by basically making system configuration also just another immutable data structure actually, so that every time you apply a system configuration change or you install a new package, you're actually creating a new version of your operating system, and you keep what you had before doesn't get lost, so that if something fails, which I think everybody has experienced before, you get to roll back to the old known state and you don't experience any strange bugs, any data loss or whatever. Have you actually, I just know that it exists and I've wanted to play around with it, but it's kind of difficult at this stage because it's not really really advanced. Do you have experience with it, and do you think it's generally a good idea? Do you think there's any future to it, or?
I mean, I know it's a good idea. It's how Netflix works. So Netflix doesn't deploy code, right? They do this thing where they have immutable deploys. They just deploy machines, and then like if it starts going up and they see that things start failing, they can just gracefully degrade and bring back the old machines. I think it's just a good design. It's good architecture. Whether the actual current state of the art is good enough for regular people to use, I don't know. I mean, this is true for even a lot of things that I demonstrate. In some sense, a lot of things I'm talking about is a little bit cutting edge, and I think there's a lot of work to be done to make it, really usable by anyone. Right there.
Okay, so I understand the immutable data structures are quite easy to work with when you have a simple situation where you have like a piece of a local state that you want to modify, then it's not a problem. But I'm wondering if it's not harder if you have a system with a lot of interactions, and if you don't have to then like force yourself to write in this awkward functional way.
So this is a problem. And so React actually, and people have, Facebook proposes this thing called Flux, which has some good ideas, I think, quite a few good ideas for dealing with this problem. The problem that you're describing is real. So if everything has to be functional and you have to organize your program around a tree, then every component has to get something from above. And it's quite strange, and I don't really like it. And actually, it's been something that we've been addressing in Ohm. And hopefully, we'll have, I'm on vacation technically right now. But when I get back, my plan was to write a blog post and sort of talk about the problem with a purely functional design, the fact that every component, people in between may have to receive data they don't want to see. But there are ways to work around it, and you can still preserve every property that I talked about.
Mm-hmm. Yeah, because the context I was thinking about this in is games. If you are writing some sort of maybe complicated game with immutable data structure, you get something like time travel for free. You can restore in the previous state and so on. But still, I would like to see some way around just holding a copy of the global objects every time.
So just to give you a really quick answer, so one way you can do it, the solution that I came up with is that you can have a component, and a component can have hidden dependencies in the global app state, so it doesn't have to receive the data from anyone. It can depend on the data itself. And so we don't break away from the global app state model. What we're introducing is this notion of end data dependencies that nobody else cares about. And this allows you to write very modular programs where you have components that have no idea what other components are doing, yet you're still in the global app state game snapshotting thing. But yeah, it's a problem, and I have a solution, and hopefully other people have other solutions. Cool. Thank you.